Right. If you remember, we were covering the discrete time Fourier transform properties, and we have seen some of the properties previously. The last thing that we have seen was the upsampling property that I mentioned thoroughly. And the situation was something like this. If you have a scaling in time, then the inverse of that scaling appears in the frequency. And that was a property from the continuous time that we already know. But in discrete time, this scaling property, this one that we see here at the top equation, is valid for only upsampling. In other words, if you divide the n by a capital N, which means insertion of zeros in between samples. That is what upsampling is. You're stretching your signal in time domain by some integer factors. Of course, it must be an integer factor, and you insert zeros. For example, if you stretch it twice, it means insertion of 1 0. If you stretch 3 times, it means you insert 2 zeros in between every other sample. For example, at the top you see a shape for an upsampling by a factor of 2. In that case, that capital N is equal to 2, and therefore what you have is, in the Fourier domain, x of 2 times omega. N times omega is 2 times omega. Since x of omega originally is a 2 pi periodic signal, x of 2 omega is automatically 2 pi periodic as well. It becomes even better than that. It becomes pi periodic. So that's a condition of 2 pi periodicity is naturally satisfied if you do upsampling. And finally, I have also mentioned that downsampling is a different alien. That is, x of 2n, for example, x of 3n. It means elimination or omitting of some of the samples. If it is x of 2n, for example, you recover one sample and eliminate the other one, then have the third one. The fourth one is eliminated, you have the fifth one, etc. You go on like that. That is a downsampling phenomenon. And if you try to apply the similar strategy and say that this is x of capital N times n, therefore, in the Fourier domain, I would expect something like capital X of omega over n, right? Or omega over 2, for example, if it's a downsampling by a factor of 2. But the problem, as I have mentioned, is about the 2 pi periodicity of capital X of omega over 2. If x of omega is 2 pi periodic, what is the period of x of omega over 2 on the omega domain? It becomes 4 pi periodic. If it is omega over 3 for a downsampling by a factor of 3, then it would be 6 pi periodic. So that's problem because if it is 4 pi periodic in the Fourier domain or 6 pi periodic, whatever, n times 2 pi periodic, in other words, then it's not 2 pi periodic anymore, which means that the Fourier transform is not that one, and it's not as simple as that. We have to consider some extra terms to compensate, and it comes from the derivations as well, but that's a complicated issue, and that's why I'm not very much into explaining it. I don't think downsampling could be better understood in a signal sense systems course. It may be understood in a digital signal processing course because it's a core concept then. Downsampling or resampling in general. It's a very fundamental concept of digital signal processing, but it's a continuation of signal sense systems. So for the time being, let's skip that downsampling part. You're only responsible for the upsampling, which is fair enough for the signal sense systems course, not the digital signal processing portion, of course. Now we have a lot of other rather difficult to understand concepts in the properties. For example, one other property that we may think of is a multiplication in time. Do you remember what multiplication in time corresponded to in the continuous time? When you multiply two signals, x of t with y of t, or let me be more precise, for example, if you multiply x of t with a cosine signal, a sinusoid at high frequency, we gave a specific name to that. Do you remember the name? Huh? Modulation. Yes, that was the communication-wise modulation. And do you remember what we were doing in the frequency domain then? We were convolving. So if you multiply in one domain, you convolve in the other domain. If you multiply x of t with cosine omega ct in time domain, that's a multiplication, then it means you are convolving the Fourier transform of x with the Fourier transform of cosine, which are two impulses, and that was carrying of the shape, the low pass shape, to the positions of the impulses at high frequencies, and we were saying that that phenomenon is the modulation phenomenon. Now, it's a similar situation here in the discrete time, but of course we have some problems because the convolution will be in continuous axis. It's not continuous time, it's continuous axis of omega, but the signals are 2 pi periodic. So what kind of a convolution can we mention, can we think of in the periodic sequences? The situation will be called, the name given to that will be a periodic convolution. That's something different than the easy continuous time case. For example, if y of n is equal to x1 of n times x2 of n, which is a multiplication in time, then what is the discrete time Fourier transform corresponding to y? Remember that we were writing the discrete time Fourier transform in this notation, e to the j omega, but that's y of omega. Now that is a 2 pi periodic convolution of two 2 pi periodic signals. And the mathematical expression is this. There's a 1 over 2 pi, and the integration is not an infinite convolution limit from minus infinity to infinity. It's not like that. It must be done in a single or in a certain amount of starting and ending point, which is of length 2 pi in the frequency axis. It may be from 0 to 2 pi, from minus pi to pi, from minus 2 pi to 0, whatever. The length is 2 pi. We know how, what this means. And we need to write the convolution expression of two signals in Fourier domain, in the frequency domain. In time domain, we were using an auxiliary variable of tau. Do you remember that? X of tau, y of t minus tau. So let me write x1 of tau and x2 of t minus tau, but it's not t anymore, it's omega. So here it is x1 of tau, and as you see, I'm using a different auxiliary variable now. It's not tau, it's theta, because it's more related with the angles and frequencies. So tau is more related to time, t and tau. Omega will be replaced by theta. That would be a better notation. And x2 of t minus tau. x2 of t minus tau, which is omega minus theta. But it is all written in the exponent because that's the notation. Okay, it's just due to the notation. This second term is nothing but x2 of omega minus theta. Okay, you can think of it like that. D tau is of course d theta now. So what we see here is a portion of the convolution, but that portion is not from minus infinity to infinity. It is a 2 pi duration. That 2 pi duration is necessary because if you apply an infinite integration, think of it like this. Here, let's think of a periodic sequence. Don't try to draw this. This is just an illustration. Okay, just watch what I'm drawing. I may even erase it from here. And now we have which is 2 pi, which is periodic, okay? 2 pi periodic, of course, in the frequency axis. Suppose this is 2 pi, and suppose that we have another low pass signal which have different shapes. This must also be 2 pi periodic, by the way, on the frequency axis. If you multiply these two, you will see that the multiplication will also be 2 pi periodic. Do you see that? Okay. And if you integrate it from minus infinity to infinity, what will you get? The multiplication, which will be something like this, maybe, I don't know. Let's imagine that it is like this. Like this. If you integrate it for all omega, what will be the value? What's the integral of this from minus infinity to infinity? Yes, it is infinity. Because it's periodic, it repeats itself indefinitely. That's why an infinite integral here at the top equation is prohibited. You cannot do that. If you integrate from minus infinity to infinity, that corresponds to nonsense, garbage. It will be an infinity. That's why we have the integration to be limited, and that corresponds to, or the name, the terminology of this thing corresponds to a circular convolution. And this circular convolution has some problems as well. It's not as easy as just flipping around one of the signals and sliding. Well, it's the same as that. That's okay. You flip around one of the sequences and slide the other one. But when you flip around and slide, you see that this one here, as well as this one that you flip around, are periodic. So when you slide this much, they become non-overlapping in the linear convolution. We know that. After some time, they become non-overlapping. And you are safe. But what if this one repeats itself here, here, and here? As well as this one repeating itself there, there, and there. So after some time, maybe this one will not overlap, but something else from here will start overlapping with this one. Another copy, a replica, will start overlapping. So things are constantly overlapping with each other. Or you may think of it like this, consider a cylinder shape. So instead of sliding, you're just rotating the cylinder, and because of that, after some point of going out, from the other side of the cylinder, some new items will come into the picture, and they will start overlapping with the existing X1 signal, for example. Suppose X2 is the flipped around and rotated, X1 is there. But if they are all 2 pi periodic, the 2 pi circular convolution is a mess, and you have to be very careful about that. You have to very carefully slide one of them and see whether after some point this one will not overlap, but the other extra term will start overlapping, and things like that. And you have to be careful about that. There is one example that I want to mention, and I will give some legends without elaborating a lot on that, because I believe that you need to spend some time to inspect the example and see why the values happen to be that way. So I will be a little bit quick, and I urge you that when you go home or after the class, you closely inspect and see that the answer is like that. Because even linear convolution is quite messy, we know that. Circular convolution is even more difficult. And the example is like this. We have one low-pass signal whose Fourier transform is given to you, okay? And it's like this. From this is pi over 2, this is pi, minus pi over 2, this is pi over 2, and this is pi, and somewhere at the right hand side around here we have a 2 pi, whatever, they continue. And the low pass is a good ideal low pass filter or a signal like this. So this is x1 e to the j omega. From minus pi over 2 to pi over 2, a band low pass signal whose Fourier transform is like this. It may be like this. I mean, in the exam you may expect a question like this. I can give you an explanation. I say that it's an ideal low pass signal whose magnitude is 1 for omega between minus pi over 2 and pi over 2. But even though I may say it like this, you must automatically append the other 2 pi periodic replicas by yourselves, even if they are not given to you. And what are they? They are here. Because around 2 pi at the right hand side, as you see, another length pi low pass sequence must appear. So the gap that you have is only from pi over 2 to 3 pi over 2. See? That portion is a zero gap. It's not a zero starting from pi over 2 and extending to infinity. Of course, other replicas are also coming into the picture. These are just 2 example 2 pi periodic replicas. And we have another signal x2 of e to the j omega, which is another ideal low pass signal, but the bandwidth is not up to pi over 2, it is up to a point in between, which is 3 pi over 4. So this is minus pi over 2, minus pi, and it's up to here, minus 3 pi over 4. It is 1. So it's a wider band low pass signal. I can again give it like this, and I may ask you to complete this first. I mean, in order to solve the rest of the questions, you must repeat them. And how do they repeat? As you see, the gap around pi will be even narrower for this case. Suppose this is 2 pi. So the other extra term will be starting from here, which is 5 pi over 4. And it also starts at minus 5 pi over 4. So a wider slot is repeating itself with a period of 2 pi. Therefore, when I ask the Fourier transform of multiplication of x1 and x2 in the time domain, so yn is equal to x1 of n times x2 of n, and the question is what is y of e to the j omega, which is the Fourier transform of the multiplication in time domain. And then you have to just circularly convolve these two shapes. Now notice that when you flip around, let's say that you flip around x2. When you flip around x2, even though you may slide, you see that they are always overlapping. There's always an overlap. There is no non-overlapping portion if you slide one of them on the other one. If the top one and the bottom one are not synchronized, if they are pi separated, then the overlap will be minimum. Some of the gaps of the top will overlap with the non-gap version of the bottom, and gaps of the bottom one will overlap with the non-zero portions of the top. Therefore, the value will be small, around pi. It will be larger around 0. And if you just carefully do it, and I don't know a way to do it carefully in the classroom, you just have to work it out, okay? Concentrate and try to work it out. And you will see that it will be like this. This is pi over 2, this is pi over 4. This is 3 pi over 4. This is pi, etc. It goes on like this. And the convolution happens to be like this, from 0 to pi over 4, it stays, which means it also stays from minus pi over 4 to pi over 4. It's a constant value, which is the maximum value when you overlap the two shapes in the center. And when you overlap the two shapes in the center, what you get will be the shape at the top. Their overlapping is equal to the shape at the top. Do you see that? When you multiply these two, the multiplication is the one at the top. The narrower one will be the multiplication result. And then you must just integrate, and I recommend that you make the integration from minus pi to pi. So what's the integral of the top shape from minus pi to pi? It is pi, yes. The integral is pi. Level 1 from minus pi over 2 to pi over 2, area is pi. So you have to divide by 2 pi, because there's a 1 over 2 pi in the beginning of the formula. Pi over 2 pi is 1 over 2. So that is the peak value, which is 1 over 2. And from pi over 3, pi over 4 to 3 pi over 4 here, the value decreases to the half. Why is it now the half, which is 1 over 4? Why is it half? Let's see. Well, you have to just slide this one by an amount of pi, and see where it goes down. Then you shift this one to pi over to this sample 0 to pi. Just draw that on top of the top one. I'll try to do it with a different color. Let's use the red color here. And around pi it will be like this. Do you see that? When you shift the bottom shape by an amount of pi, at the top it will be like this. So what is the intersection of the black and the dashed red one? The intersection will be only here, the non-zero portions. And this time, of course, the area, integral area calculation can be carried out from 0 to 2 pi. Let's only focus to the right-hand side. And how much is that? Pi over 4 portion comes from here. Another pi over 4 comes from here. The total is pi over 2. Divided by 2 pi, it becomes 1 over 4. And that's what I'm going to write here. That's the value 1 over 4, that it goes down. And it stays the same from here to here. And it inclines again to 1 over 2 and stays the same, and then goes down. At the other side, at the negative side, the situation is just the symmetric. Like this. So that is the shape. This is the shape that you get. Why does it stay the constant for the minimum of 1 over 4 level? Because notice here the red shape. If you slide this red dashed plane to the right a little bit more, you will see that the area here will decrease, but the area here will increase. Or if you go left, the area here will increase, but the area here will decrease. That increasing and decreasing will correspond to the same amount in the total area, which is precisely equal to pi over 2. And if you further divide it by 2 pi, you will get 1 over 4. That's why we have a level of 1 over 4 here. And at the top we have a level of 1 over 2 here. And in between, it's a linear decay. As I say, it may be a little bit complicated to work it out. You have to be just careful. It's not difficult, but it's cumbersome, and you have to be careful about what's going on in order to properly solve questions. Okay. Now another property I will have to continue. Yes.
Why the first bridge is up to pi over 4?
Beg your pardon? What are you asking?
So the y.
Yes.
So it continues being 1 over 2 up to pi over 4, right?
Yes.
Why is it pi over 4?
Because after pi over 4, after a shift more than pi over 4, the gap, another gap will start to contribute from the other side. That's what I'm telling you. I have been telling you all the time. I mean, it's difficult for me to just do it here. It may be like you may draw it on a transparent sheet, flip it around, which is the same. Don't flip around because they are symmetric. Just draw one of the shapes on a transparent sheet and put it on the other one and start sliding and see what's going on. That's the only thing that I can recommend for the time being. Now, the other property, it may be a good idea to use some digital tools for that, sliding tools, but I'm not very keen on using those things. Although I'm using a computer right now, perhaps it's easy to show with some tools, but I don't have those tools. I don't know what they are. Any help is welcome for graphics, sliding and putting overlapping, because it may be a good idea to use such digital techniques to better explain convolution, which requires a lot of sliding and overlapping things. So, the next property is the duality property, which is, I'm just giving the failing properties. The properties that are normal, they are normal, we all know them, they are not difficult, they are the same in continuous time and discrete time, but the difficult ones are the ones that I'm trying to emphasize here. Duality is one of them, and as you see, you don't really have a duality in discrete time Fourier transform, because the signal is discrete time, its Fourier transform is continuous. So when you take the continuous signal in Fourier domain as a time signal, then it's a continuous time signal whose Fourier transform will not be discrete. So what's going on? One domain is incompatible with the other domain. In the continuous time, it was a time signal, continuous, and the Fourier transform is a frequency signal, continuous. So you may interchange their roles. You may consider the frequency signal as a continuous time signal, and the Fourier transform will be like the time signal in the other case. But here, there is a problem. One domain is discrete, the other domain is continuous. So what sort of a duality can we think of? We must think of the situation like this. The duality exists only in discrete time Fourier series. Okay, unfortunately, it's not the discrete time Fourier transform that we can think of. So if you have a time domain signal f of n, which is periodic, you see, then we know that we have the Fourier series coefficients of them. And if the periodic signal f of n is periodic with n, capital N, then what is the period, or how many Fourier series coefficients do we have? You may or may not remember from the previous lectures. You have capital N distinct Fourier series coefficients. Okay, let me tell you that. But they are also periodically repeating themselves. You remember? A1 is equal to A capital N plus 1. A2 is equal to A capital N plus 2. The Fourier series coefficients were also repeating themselves. So what you really get is the Fourier series coefficients of this periodic signal, which let's indicate by G of k. That is also periodic with capital N. These are the Fourier series coefficients. It's not the discrete time Fourier transform, because for the discrete time Fourier transform we don't really have the duality property that we can think of. Now let's take these Fourier series coefficients G of k and make them like a periodic time signal G of n. Just let the axis be not a k axis but an n axis. Then it's gonna be automatically a periodic time domain signal with a period capital N, of course, and the Fourier series coefficients of these ones will be equal to 1 over n times these, which are f, k. Do you understand the situation here? The left-hand side, you have a time domain signal and you have the Fourier series coefficients. Let's plot those Fourier series coefficients on a discrete n-axis, make them a discrete time signal like g of n. Then the Fourier series coefficients of this one will be related with the original time signal f. They are just 1 over n, 1 over capital N times f, which is, of course, again, periodic with capital N. So this is the Fourier duality that we can think of in discrete time. Yes, you have a question.
Hocam bu FN dediğimiz onların Fourier serisinin Fourier seri olmuş oluyor.
In the original, this is a signal. It's a discrete time periodic signal. This discrete time periodic signal. Therefore, it has Fourier series coefficients.
GK'li onların mı?
Yes, GKs are the Fourier series coefficients of f. And now this time take those GKs which were originally the Fourier series coefficients, but let's consider them as the signal, the periodic discrete time signal. Make it g of n. Then the Fourier series coefficients of them will be related with the original time signal, discrete time signal f. This is the duality property.
Bunu periyodik sinyallerin Fourier transformunu bulmak için kullanacağız.
Nope. This is just the duality property that may help us to find the Fourier series coefficients of some periodic discrete time signals. Okay, let me give an example. And maybe you will recognize why we may need to use this duality property. Let's assume that the periodic signal that we have is an awkward, a strange signal of this form. It is equal to 1 over 9 sine 5 pi n over 9 over sine pi n over 9 for all n different than L times 9, not an integer multiple of 9 in other words, and it's automatically equal to 5 when n is an integer multiplied by 9. So the DC value is 5. I'm writing the second term separately because if you say n is equal to 0 or an integer multiple of 9, then the denominator, this sign, will become a 0. And the numerator will also become a 0. So it will be a 0 over 0 ambiguity for the DC. Just to avoid that and just to avoid the utilization of Hospital's rule, I'm putting a 5, which is the value that we have. Now, sorry, it's not 5, of course, divided by 9. Using the Hospital's rule, you have a 1 over 9 term coming. Sorry, there was already a 1 over 9 term. So 5 times 1 over 9 is 5 over 9. This is the DC value. For all the others, you have the top shape. Now, you may or may not remember this, but it looks like the Fourier series coefficients of something that we already know. And that's where the duality thing comes into the picture. If you had a different signal, let's call that signal a different signal y of n, to be equal to 1 for a duration from -2 to 2 and 0 for a duration, greater than the magnitude of n, okay, or at last, and less than or equal to 4. And this is a definition between -4 to 4. which is consisting of 9 items, and it is periodically repeating itself with a period of n is equal to 9. So from minus 4 to 4, it's a rectangular box from minus 2 to 2. From minus 4 to minus 2, it is zeros. From 2 to 4, it's again zeros. And from minus 2 to 2, it is ones. So it's a rectangular box shape of length 5, and it is repeating itself with a period of 9. If you're curious, you may just plot it if you wish. It is like this: at 0, 1 and 2 it is ones, and from minus 2 to 2, therefore it is ones, and then 3 and 4 is zeros. 5 and 6 are also zeros, and then you have 7, 8, 9, which is the center of the next rectangular shape. So this center is now repeating itself here as well. And then 4 more zeros, and then 5 more non-zeros, ones. So this is a periodic signal that I have previously called y, like this. And the Fourier series coefficients of this y of n, I'm going to call them bk's, are equal to, of course, the one that I gave at the top, which are 1 over 9 sine 5 pi k over 9 for all k different than an integer multiple of 9, and 5 over 9 for all k equals to an integer multiple of 9. So these are the Fourier series coefficients of this signal. And from the duality property only you can solve this question. What are the Fourier series coefficients of this thing then? Which is, again, a 9-periodic signal. Since it's a periodic signal, it doesn't have the Fourier transform, or you may just insert impulses in the position of the Fourier series and give me the Fourier transform as well. Okay, I can also ask you that. But let's forget about the Fourier transform. It's periodic, therefore I'm asking you the Fourier series coefficients of them. What are the Fourier series coefficients of x then? So I will say that this x of n is equal to this b of n, and therefore the Fourier series coefficients will be equal to what? Using this property, just tell me the result. 1 over n, which is 1 over 9 times this y signal, y of k, exactly, because it's in the Fourier domain. The Fourier series are indicated by an index k. Y of k. That's it. Or you can even write it using the formula at the top. Yk is equal to, or it's equal to 1 over 9 times 1, which is 1 over 9, when k in magnitude is less than or equal to 2, and it's equal to 0 if it is greater than 2, less than or equal to 4, with a period of n is equal to 9, of course. So this is the answer, 1 over 9. From minus 2 to 2. So a minus 2 is 1 over 9. A minus 1 is 1 over 9. A0 is 1 over 9. A1 is 1 over 9. A2 is also 1 over 9. And the others within the range from minus 4 to 4, from a minus 4 to a plus 4, the others are 0. These are the Fourier series coefficients. Now, you must ask yourselves this question. What if I ask you the Fourier transform instead of the Fourier series coefficients? What will be your answer? more or less the same. It's similar but not the same because I'm not asking the Fourier series coefficients. I'm asking the Fourier transform. You must just replace these Fourier series coefficients with impulses, arrowed impulses, on the frequency axis, not on the integer axis. On the frequency axis, you must insert impulses. And the magnitudes of the impulses must be 2 pi times these, 2 pi times 2 pi over 9. So they will be the Fourier transforms. But of course you must evaluate what frequency they correspond to, so that you make sure that the impulses are at the correct position along the spectral axis, along the frequency axis. But that's a different story. This much, I guess, will be enough for the time being in terms of the property of duality. So we don't have a duality property in the Fourier transform. We have a duality property in the Fourier series representations. And now the next, let's start by writing down the next because it's not very difficult. The situation is like this. How can we solve the difference equations? Or how can we relate the Fourier transform of a system, which is the frequency response? It's not the impulse response, it's the frequency response, which is the Fourier transform of the impulse response, of course. How can we relate, therefore, h of e to the j omega to the input-output difference equations? How can we relate them? Let's start by the difference equations, and from there can we construct the frequency response h of e to the j omega expression. Do you remember how we did it in the continuous time? In the continuous time we had the differential equations, and for each derivative d by dt we replaced in the Fourier domain with the j omega. Every d by dt was a j omega, and then we obtained y of omega divided by x of omega. Within parentheses you can do that, and y omega over x omega is equal to h omega, which is the Fourier transform or the frequency response of the system. That's how we did it. We are going to do something similar, and an example, the first example before the break, will explain everything, I suppose. Suppose we have a first order system like this, and I'm asking you the frequency response or the impulse response. The impulse response is even easy for this case. Let's write the Fourier transform of both sides of the equation. Here you have y of e to the j omega minus 8 times. When you shift by a factor of 1 in time domain, the Fourier transform is e to the minus 1 times j omega times y of e to the j omega. You see that? This is the Fourier transform of its top is equal to x of e to the j omega. Now let's put the right hand side and the left hand side of the equations to y and x parentheses. At the left hand side we have y e to the j omega parentheses 1 minus a e to the minus j omega is equal to x of e to the j omega. And now y e to the j omega over x e to the j omega, which is of course equal to h e to the j omega. In the Fourier domain, it's not convolution that you do, it's the multiplication. You multiply h by x in frequency domain to obtain y. And this one is equal to 1 over 1 minus a e to the minus j omega. Okay? And it was the first example that we did for discrete time Fourier transform. What discrete time Fourier transform was that? What was the time signal corresponding to that? Do you remember that? Huh? a to the power n times u of n. The Fourier transform of that was the one at its top. So what do we have now? We have difference equations at one side of the triangle. We have the Fourier transform h of e to the j omega at the other side of the triangle, and we have h of n at the other side of the triangle. So I may give you, the question may start from any of these. I can give you, for example, the impulse response of the system, and I ask you, what is the difference equation there? So how are you going to do that? Huh? No, it's not duality. What you need to do is, if I give you h of n, just find h of e to the j omega, the Fourier transform. Go left. And from the h of e to the j omega, say that h of e to the j omega is equal to y e to the j omega over x e to the j omega, and write it like this. Oops, sorry. Then write it like this, and expand from here to here, and take the inverse Fourier transform of both sides of this equation. From here to here, now you get the difference equation. It may start from the difference equation and it may end at the impulse response, or it may start from the impulse response and end at the difference equation. And in between you use the Fourier transform, of course, h of e to the j omega, and say that h of e to the j omega is equal to y e to the j omega divided by x e to the j omega, of course. The same things that we did in continuous time. In the continuous time, the legs of this triangular shape was h of j omega, h of t, and here you have the differential equation, not the difference equation. But it's the same story. Okay. Now we can give a 15 minutes break, and this thing concludes the chapter of discrete time Fourier transform. We are going to start with a new chapter in the next hour.